In this session, I'm going to teach you deterministic finite automata. First of all, we'll see the learning objectives of finite automata. It is a mathematical model of a digital computer. It is used as a language acceptor. It is mainly used in pattern matching tools like LEX. It makes the student to design deterministic finite automata for accepting the string and for rejecting the string. It checks whether the string is accepted or not. In previous session, we have seen what is finite automata and its applications of finite automata. Here we have types of finite automata. Finite automata has been classified into two types. One is deterministic finite automata, we call it as DFA. And another one is non-deterministic finite automata, we call it as NFA. Deterministic finite automata consists of only one moves for each input symbol. Non-deterministic finite automata consists of more than one moves for a same input symbol. Here in this session, we'll see deterministic finite automata and how to represent it in graphical way, and we have to check whether the given string is accepted or not, and then we have transition function. First we'll see DFA with example. So here we have transition diagram. It consists of states Q0 and Q1. Here we have input symbol as 0 and 1. From Q0 state, using input symbol 0, it goes to Q1. From Q0 state, using input symbol 1, it goes to Q0. From Q1 state, using input symbol 0, it goes to Q1. From Q1, using input symbol 1, it goes to Q0. Here we have represented it in transition table. At each step, we have transition from one state to another state using one input symbol. So we call it as DFA. If we have more than one input symbol from one state to another state, we call it as NFA. Here we have architecture. In strings are represented in input tape. We have to process the alphabet of a string. It has to be given to the finite automata. It checks whether the given string is accepted or not. To accept the string, all the input string is scanned and the last state is accepting state. To reject a string, all the string is scanned and the last state is not accepting state. The string has to be processed one by one. Here we have sample transition graph. The states are Q0, Q1, Q2, Q3, Q4 and Q5. Alphabet is A and B. Using the alphabet A and B, it moves from one state to another state. We call it as transition. Here we have only one transition for each input symbol. Q0 is considered as the initial state here. Q4 is considered as the final state or accepting state. For every state, there is a transition for every symbol in the alphabet. Next, we will see the example for accepting the given string. The string has to be represented in the input tape. Alphabet of the string has to be processed one by one. In this, the transition graph which is mentioned before, using this transition graph, we have to process the string. First, we have to start it from Q0 state. That is the initial state. From Q0, we have to process the first input alphabet, that is A. From Q0, using A, it goes to Q1. Next alphabet is B. From Q1, using B, it goes to Q2. Next alphabet is B. From Q2, using B, it goes to Q3. Next alphabet is A. From Q3, using A, it goes to Q4. Finally, it reaches the acceptance states. Since Q4 is the final state here, so we call the given string is accepted because it reaches the final state. Now we'll see One example for rejecting the input. Here we have considered ABA as the input string which is mentioned in input tape. We have to process the alphabet one by one. Here we have ABA. So first of all we have to process the first alphabet, that is A. We have to start it from initial state, that is Q0. From Q0, using input A, it goes to Q1. Next alphabet is B. So from Q1, using input alphabet B, it goes to Q2. Next alphabet is A. From Q2, using the alphabet A, it goes to Q5. So we have finished scanning the input string, but it doesn't reaches the final state. Q5 is not a final state since Q4 is the final state. Hence we say the given string is rejected. Next we have formal definition of DFA. From these things we derive DFA. It consists of 5 tuples, that is Q, summation, del, Q0 and F, where Q is the set of states and summation is the input alphabet. Del is the transition from one state to another state, that is represented by Q into summation. Using the state, from state, using the alphabet in summation, it goes to some other states. So that is represented by Q into summation equal to Q. Q0 is the initial state or start state. F is the final state or accepting state. So this is the formal definition of DFA. Here we have seen the sample transition graph. In this transition graph, the set of states are, that is Q equal to Q0, Q1, Q2, Q3, Q4 and Q5. The input alphabet in this transition graph consists of A and B, that is summation equal to A and B. Next one is the initial state. In this transition graph we have Q0 as the initial state. Final state is Q4 in this transition graph. So we have F is equal to Q4. F should be a subset of Q. Transition graph can have more than one final state. The final state may be a set of states, but the initial state should be the only one. Now we will see the transition function. Transition function is represented by using del symbol. So del of states comma input alphabet equal to current state. That is, here we have to start it from Q0. From Q0, using input alphabet A, it goes to Q1. That is represented as del of Q0 comma A, which is equal to Q1. Next we will see some other example, that is from Q0, using input symbol B, it goes to Q5. So del of Q0 comma B is equal to Q5. From Q2 state, using input symbol B, it goes to Q3 state. The transition function for this one is del of Q2 comma B is equal to Q3. Here we have drawn the transition table for the transition function. Here we have transition graph. In this, from Q0, using input symbol A, it goes to Q1. From Q0, using input symbol B, it goes to Q5. From Q1, using input symbol A, it goes to Q5. From Q1, using input symbol B, it goes to Q2. From Q2, using input symbol A, it goes to Q5 state. From Q2, using input symbol B, it goes to Q3 state. From Q3 state, using the input symbol A, it goes to Q4 state. From Q3 state, using the input symbol B, it goes to Q5 state. From Q4 state, using the input symbol A, it goes to Q5 state. From Q4, using the input symbol A, it goes to Q5 state. From Q5, using the input symbol A, it goes to Q5 state. From Q5 state, using the input symbol B, it goes to Q5 state. So this is the transition table for the transition graph. Likewise, we can define DFA since each transition table, next we will see the extended transition function. Here we have example, that is AB is considered as the input string. The extended transition function is represented as del power star. So here we have to process two input symbols at a time. So from Q0, that is Q0 is the initial state, Q0 we have to process the input symbol A and B. We have to check to which state it goes. From Q0, using the input symbol A, it goes to Q1. Next we have to process the next input symbol, that is B. From Q1, using B, it goes to Q2. The transition function, extended transition function is del power star Q0 comma AB is equal to Q2. Next we will see the transition function for the string A triple B double A. We have to start it from Q0. So from Q0, using the first input alphabet A, it goes to Q1 state. From Q1 state, we have to process the next input alphabet, that is B. From Q1, using B, it goes to Q2 state. The next input alphabet is B. From Q2, using B, it goes to Q3. The next input alphabet is again B. So from Q3, using input alphabet B, it goes to Q5. Next, the input alphabet is A. From Q5, using the input alphabet A, it goes to Q5 itself. The next final input alphabet is A. From Q5, using the alphabet A, it goes to Q5. So the transition function for this one is del power star of Q0 comma A B B B A A is equal to Q5. Next we will see some other example, that is the string BBA. We have to process this string from Q1. So from Q1, the first alphabet is B. From Q1, using B, it goes to Q2. The next alphabet is B. So from Q2, using B, it goes to Q3. Next alphabet is A. From Q3, using the input alphabet A, it goes to Q4. The extended transition function for this is del power star of Q1 comma BBA is equal to Q4. So far in this session, we have seen what is deterministic finite automata and how to represent the deterministic finite automata and transition graph for this one, and we have to check whether